Let's explore how digital retail systems have evolved and how we build them today. Looking at the big picture, we are seeing a major shift from basic scripts to robust ecosystems. In the past, e-commerce platforms were essentially built on simple scripts. These old scripts were very linear. They simply took transactions, processed them, and moved data around. But as businesses grew, this wasn't enough. Today, through digital transformation, we require a modern multi-layered ecosystem. Notice how this modern approach is neatly organized into specific layers for your UI, business logic, and core data. This separation is what makes the system robust, maintainable, and expandable. To build these modern systems, we rely heavily on object-oriented programming, or OOP. The core intuition behind OOP is brilliant. It allows us to map real-world entities directly into our code. Instead of just treating software as a pipeline for data, we look at our physical retail store and build a code model made of objects. We treat things like products, customers, inventories, and transactions as individual objects. Every single one of these objects has three distinct characteristics: its state, which is its data, its behavior, which are its actions, and its overall life cycle within the system. For this architecture, Python is an outstanding choice. It provides an excellent balance. It gives architects a clean syntax and high-level abstraction, freeing you from worrying about low-level memory management so you can focus on system structure. It also natively supports advanced architectural tools like multiple inheritance and decorators, which keep our code flexible as business needs shift. Of course, building this involves tackling major engineering challenges like managing time-sensitive order updates while keeping the business logic safely separated from raw data. To handle this, we utilize a domain-driven approach. Our goal here is twofold. First, we want high cohesion, which means a specific module does its one job exceptionally well. Second, we want low coupling, ensuring that different parts of our system remain independent. The golden rule to remember here is, if you change your shipping cost logic, it absolutely should not break your user login system. To achieve all of this, we build upon the four fundamental pillars of OOP. Let's walk through them. First is abstraction. Abstraction lets us define what a system must do before we worry about how it does it. In Python, we use the ABC module to establish a strict contract. Look at this base product. It dictates that any product in our system must have a way to calculate tax. It doesn't matter if it's a physical book or a digital movie. The system knows it can calculate the tax, even though they will inevitably use different math to get the final number. The second pillar is encapsulation. This is about bundling your data and your methods together while hiding the sensitive internal details. For example, in our product class, the actual price data is hidden. To interact with it, we route access through a property decorator. This lets us enforce strict business rules, ensuring, for example, that the price is strictly greater than 0. Next, we have inheritance, which establishes an is-a hierarchical relationship. A physical product is a base product, therefore, it automatically inherits core attributes like name and price from its parent class. But it can easily add its own unique requirements like physical weight and shipping dimensions. The fourth pillar is polymorphism, which translates to many forms. This means different objects can receive the exact same command but respond in their own unique way. Think about our checkout system. It simply calls a process payment command. It doesn't actually need to know if it is talking to a credit card processor or a PayPal processor. In Python, this is called duck typing. If it walks like a payment processor, we treat it like one. This results in a highly decoupled system, allowing you to add Apple Pay tomorrow without rewriting your entire checkout logic. Finally,
Before we write a single line of this code, we plan it all out using system blueprinting, like UML diagrams. These maps clearly visualize the classes, their internal data, and the relationships between entities like customers and orders. Now that we understand how OOP helps us model our individual business components, we need a way to organize this entire ecosystem on a server. To keep everything organized, professional platforms use a three-tier architecture, which we will look at next.
To keep the system organized, a professional platform uses a three-tiered architecture. This separates the presentation, the logic, and the data into distinct layers. The first tier is the presentation tier. This is exactly what the user sees, handling user actions and displaying data using tools like Flask or Django templates. Next, we have the application tier. Think of this as the brain of the system. It processes all the business logic and computational tasks using Python classes and design patterns. Underneath it all is the data tier. This is where your information is stored permanently, utilizing databases like PostgreSQL or MySQL to manage data integrity. Why do we split it up like this? It allows for independent scaling. If thousands of people suddenly visit your site, you can scale up just the presentation tier to handle the traffic spike without touching the underlying database or business logic. Now, over on the database side, it is vital that our Python classes map correctly. Instead of putting everything into one big redundant table, which causes errors, we use database normalization to break data into smaller, connected tables. Take a user and address, for example. Rather than saving the address directly on the user, we use a many-to-many relationship. This efficiently handles cases where different users live at the same address or one user has multiple addresses. We even break addresses down into separate city and country tables to prevent typos and keep shipping math accurate. We use several common mapping types here. For instance, user to order is one-to-many, while product to category is many-to-many. A cart to cart item is another one-to-many relationship. Looking at the code level, the product class is the foundation of our store. Using the ABC module, we define a base product that sets the rules. Notice the decorators used for validation. If someone tries to set a price less than 0, the system raises a value error. This is a practical everyday application of encapsulation. From this solid base, we branch out. A physical product adds a weight attribute for shipping, and a digital product might add a file download URL. Finally, let's look at aggregation in inventory management. An inventory has a collection of products, but these products are independent. If the inventory list is deleted, the product data still remains safely in our system. We use aggregation instead of composition because we want product descriptions to survive even if an item drops out of a specific stock list. The key takeaway here is that organizing your system into distinct tiers and normalizing your data structures makes complex applications scalable, robust, and much easier to maintain. Next, we'll dive into how the user class specifically manages security and role-based permissions within this architecture. Let's look at how we handle identity and access management within our system's architecture. Starting on the left, the user class manages who is using the system and, crucially, their security. Sensitive data like passwords are never stored as plain text. Instead, the user class uses a private attribute, like this password hash here, marked with double underscores. When a user signs up, their plain text password is passed through a secure hashing method. Then, when they try to log in, the provided password is evaluated using a compare function against that secure hash. If they match, the user is authenticated. We also use inheritance to establish role-based access control.
Notice how the admin user class inherits from the standard user class. This means the admin gets all the standard user powers, but it adds special administrative abilities, like adding new products or updating inventory. This reuses code effectively while keeping administrative tools locked down. Moving over to the transactional engine, let's talk about the shopping cart logic. The shopping cart acts as a buffer where items sit before checkout. Inside this buffer, we store multiple cart item objects which hold the specific product and its requested quantity. To track these items efficiently, we use a dictionary for storage. The key for this dictionary is the product ID. Because of this dictionary structure, when you add an item, it's very fast to check if the item already exists. If the answer is yes, the system simply increases the quantity. If the answer is no, it will add a new item to the cart. Next, we have the logic for calculating totals. Each cart item knows how to calculate its own subtotal, which is just the product price multiplied by the quantity. Then, the shopping cart simply calculates the final total by summing up all of those individual subtotals. Modern carts can also provide insights directly to the user interface, utilizing advanced calculation and statistics. For example, to find the mean or average price of the cart's contents, we use this formula. Here, mu represents the mean price. We calculate it by taking the sum of the price of each individual unit and dividing that by n, which is the total number of units. The cart can also figure out the median price. First, it will sort all the item prices from lowest to highest. If there is an odd number of items, the median is just the exact middle value. If there is an even number of items, it calculates the average of the two middle values. The ultimate takeaway here is that by encapsulating specific data and operations inside dedicated classes like user and shopping cart, our application remains highly organized, secure, and performant. Now that we have our cart logic squared away, we will move on to see how the system seamlessly processes payments using flexible, secure interfaces. Matmeta ka money.
Payment processing must be highly secure and flexible, which is why we use a payment interface approach. By utilizing Python's ABC module, we define an abstract payment class that mandates a process payment method. Specific providers like Stripe Processor or PayPal Processor then implement this method with their own specific API logic. Because the checkout class only cares about the general payment interface, we can easily add a new payment method like crypto without changing any of the checkout code. This is a perfect example of low coupling. Now, some business rules change frequently, like shipping costs. Using massive if-else statements for every possible shipping scenario creates messy, hard-to-maintain code. Instead, we use the strategy pattern. Here, the order object is given a shipping strategy at runtime. We might use a standard strategy that calculates a base fee of $5 plus 50 cents per kilogram, an express strategy for $15 plus $1 per kilogram, or a free strategy that always returns a $0 cost for high-value orders. Because these are separate classes, adding a new method like drone delivery just requires writing one new class. We can apply this exact same pattern for discounts, applying specific rules to a cart based on the user's role. An order goes through many stages, and certain actions are only allowed at specific times. For example, you absolutely cannot ship an order that hasn't been paid for. To handle this smoothly, the state design pattern manages this life cycle by turning each state into its own class. When an order is new, it's in the pending state. From here, it can transition to paid or cancelled. Once it reaches the paid state, it can transition to shipped. Notice how going straight from pending to shipped state is strictly not allowed. Once it's shipped, it's on the way and can transition to delivered, but it can no longer be cancelled. In our code, the order class keeps a reference to its current state object. When you call order.ship, the order just passes that request to the current state. If the state is pending, the system returns an error. If the state is paid, the object handles the logistics and moves the order to shipped, ensuring our business rules are strictly followed. As the system grows, we need to manage global resources like database connections. We use the singleton pattern to ensure only one instance of a resource exists. In multi-threaded systems, we make sure it is thread-safe with a locking mechanism so two parts of the program don't try to create a connection at the exact same time. We also use context managers with the with statement. By using special Python methods called enter and exit, we ensure that resources are automatically opened and then properly closed, even if the program runs into an error. A professional project is organized into modular packages. The structure separates core logic, sales logic, and checkout logic. The pyproject.toml file manages our metadata and dependencies, ensuring every developer has a consistent environment. Because the system is modular, it is easy to unit test one piece at a time. We can use mocking for external services, like pretending to be Stripe so we don't spend real money during tests. To handle high performance, we implement the flyweight pattern to share data and save memory alongside aggressive caching with Redis and CDNs. Engineering a scalable platform requires moving away from a rigid database-first mindset to a flexible objects-first approach. The most important takeaway for a professional engineer is to always utilize contract-first design, defining clear interfaces to keep components independent and ready for future